Welcome back to another episode of Science with Surback. Today what we're going to be talking about is formula weights, and we're also going to be talking about stoichiometry. So a couple of objectives that you should be able to accomplish by the end of this lesson is calculate the formula of a weight of a substance given its chemical formula, and you should calculate the molecular weight of a molecular substance given its formula. And then you should also be able to calculate the volume of a amount of substance required to react with a given number of grams of substance. And then you should be able to also calculate the concentration or mass in a particular reaction. So let's go ahead, let's get started with our formula weight. So formula weights here, they are defined as the sum of atomic weights for the atoms shown in the chemical formula. Now, molecular weights, the real similar definition here, but it's just defined as the sum of the atomic weights of the atoms in a molecule as shown in the molecular formula. Now, really the only difference here between molecular and formula weights is if we're dealing with an ionic versus a covalent compound. Other than that, they get to be solved in a very similar way. So some of our steps here used to calculate these weights is, number one, use the periodic table to determine the atomic weight of each element. Step number two is to multiply the atomic weight by the subscript of that atom in the formula. And then the last step is to just add all the molecular weights from steps 1 and 2. Alright, so we'll go over an example here down below. So we have calcium nitrate, and so what I like to do here is I like to just list each of the elements involved. And so in this particular formula of calcium nitrate, I have Ca, I have N for nitrogen, and then I also have O for oxygen. And then I just go through, and for each of these elements, what I do is I find them on the periodic table and I write down their atomic weight. So for calcium, Ca, I go and I find calcium, and we use, in this class, we use 2 decimal places. So this is going to be 40.08 AMUs. So we have 40.08 AMU times the number of calciums we have in our formula. Well, we only have 1, so we multiply that by 1, and so we would end up for calcium getting 40.08 AMU. Now for nitrogen, we do the same exact thing. So we go over, we find N for nitrogen, and we see that it has an atomic mass of 14.01. So we end up with 14.01 atomic mass units times the number of nitrogens we have. Now we have to be careful because we have 1 N that gets multiplied by 2. So it is actually 14.01 times 2. So most of you can probably do this in your head, but just to double check here, if we have 14.01 times 2, we get 28.02. And again, we want to keep our 2 decimal places going here, so we're going to say 28.02 AMU. And then we get down to O for oxygen. Same thing, we look up O for oxygen, and we find it has an atomic mass of 16.00. So we write down 16.00 AMU, and we multiply it by the number of O atoms we have. Again, we have to be careful because inside here we have 3 O's times 2. That's a total of 6 oxygens. So what we do here we put in 16.00 times 6, and we get a value of 96. Now, to keep consistency here, I'm going to put 96.00 AMU. And so to find the overall formula weight of calcium nitrate, what we're going to do is we're just going to add these together. So we're going to add 40.08 plus 28.02 plus 96. All we did is we added those up. And so what we end up with for our formula weight is 164.10. So the formula weight here would be 164.10. And again, I added that decimal there to give us 2 decimals. So again, all we do is we find the atoms, we find the weight of that atom, and then we add all of those atom or those weights together. Okay, so moving on here, we're going to need to utilize that to be able to talk about percent composition. So for percent composition, we're going to start out here with just a simple definition. So the percent composition is just defined as the percentages by mass contributed by each element in the substance. And that's fine and dandy that we have that definition, but more important for us is a formula. And so in this formula, to find the percent composition of the element, and I'm just going to call that the percent of each element. But to do this, all we need to do is we need to find out the total atomic weight contributed from the element itself. So I'm going to abbreviate this, total atomic weight contributed. I'm just going to abbreviate that as CONT, contributed by one element. All divided by the entire atomic weight of the compound. Now, all of this here, I ran out of room here, but all of this gets multiplied by 100 to be able to express this as a percent. And so what we have down here is a way that we can go through steps to be able to find the percent composition. So step 1 is to determine the molecular or formula weight of the compound. And I should clarify here up above on the formula, this is the atomic weight of the compound itself. That should be on bottom. Hopefully that didn't confuse anybody. But again, step 1 is determine the molecular or formula weight of the compound. Step 2 is divide the total mass contributed of each element by the total molecular or formula weight of the compound. And then the last step here is multiply by 100. Again, that's the part I had to squeeze in there because I ran out of room. So our example down here, we want to calculate the percent of carbon or percent by mass of carbon in this sugar molecule, C12H22O11. So again, what I like to do is I like to list out each of my substances involved to be able to find our atomic weight of this particular compound. So again, we start out with carbon, C. We find that it has a atomic mass of 12.01 AMU, and we multiply it by the total number of carbons, which is 12. And so if we plug this into our calculator, we have 12.00 times 12.01 times 12, and we end up with 144.10, 12 AMUs. Now we do the same thing for hydrogen. And I said we round to 2 decimal places, but we make one exception, and that is for hydrogen. For hydrogen, we're going to keep at 3 decimals, so that atomic weight for each and every hydrogen is 1.008, and we're going to multiply it by the number of hydrogens that we have, which is 22. And so in our calculators, once more, we're going to put 1.008 times 22, because that is the number of atoms we have. And we're going to round this to 22.18. So we have 22.18 AMUs. And then we go down to our oxygen here. And again, it's just like the last time we saw oxygen. It has an atomic mass of 16.00 AMU times our total number of oxygens, which is 11. So again, we take this and we do 16 times 11, and we end up with a value of 176. And to keep consistency here, I'm going to have 176.00 AMU. And so all I need to do now to find the total overall formula weight of our compound, our sugar compound here, is just add these together. So in my calculator, I'm going to take 144.12 plus 22.18 plus 176.00. And I end up with a value of 342.30 AMUs. Okay, so that's our overall weight for our sugar compound here. Now, we only want the percent of carbon. So to find the percent of carbon, what we need to do is we need to take the mass of carbon, or that carbon contributed, and we need to have the total mass carbon contributed. So right here, this is 144.12 AMU divided by the total mass of this sugar compound, which is 342.30. So we end up with 342.30 AMU, and then we multiply that by 100. Okay, so in my calculator, what I'm going to do here is this. I am going to take 144.12 divided by 342.30, press enter, and then I'm going to multiply it by 100 so I can express this as a percent. Now, if we go by the multiplication rules, we should actually have 5 digits in our answer if we go through the protocol here. And so the percent of carbon, what this ends up being is 42.103. So this is 42.103% carbon. So now with the knowledge of molecular weight and percent by mass, we can transition to the chemical mole. So we'll transition now to the chemical mole and get a little bit more in depth of why that business there is so important. So what the chemical mole is, or what it's defined as, is the number of particles contained in one of a formula or molecular unit. And so what the chemical mole does is it allows for a convenient measure of chemical quantities. Now for us, the chemical mole, or 1 mole, is going to be equal to 6.02 times 10 to the 23rd particles. And the 6.02 times 10 to the 23rd particles is what we call Avogadro's number. And we can use Avogadro's number to convert to and from things or to and from particular particles. So let's take this for example. Let's say we want to know the number of moles in a sample of carbon dioxide that contains 9.00 times 10 to the 23rd molecules. Well, what we have, our conversion factor here, is this. 1 mole equals 6.02 times 10 to the 23rd anything. It's very similar to saying 1 dozen always equals 12, but 1 mole equals this exact number. So what we do here on our conversions is we always start out with what is given. So we have 9.00 times 10 to the 23rd, and I'm going to abbreviate molecules as MOLC just to save some space. Now I draw my conversion factor, and again, what the unit I want down in the diagonal here is the same unit I have up top. So we want molecules to cancel, and we want to go to moles. Now, how they abbreviate moles is just MOL. And so we go back up here. 1 mole of anything is always going to equal this Avogadro's number, or 6.02 times 10 to the 23rd. So again, the values here is 1 mole. Again, mole is always going to be 1 in these cases. And then the number of molecules here in 1 mole is 6.02 times 10 to the 23rd. Now, if we grab our scientific calculator here, and we start out and we type in 9.00 times 10 to the 23rd, and I'm always going to put it in parentheses. And then the other thing that I want to show you here is this. You can type in times 10 and use the root symbol to type in the power, or if you have a TI-30 Texas Instrument calculator, you can just hit the second button. You can hit right here where it says EE written in that painted on letters. You have EE, it gives you 1E. That already says times 10, and then you just type in what your power is. So in this case, it's going to be 23. Now, we divide it, in this case, by 6.02 times 10 to the 23rd. Again, we have another number in scientific notation, so we have 6.02. We put that in parentheses, and then again, times 10. You can just hit second, EE, and then 23. I press enter, and the value here for the number of moles, after we round it, would be 1.50 moles of CO2. And again, this would be 1.50 moles of CO2. So another important thing here is this. Yes, the number is important, but also, hey, what substance are you dealing with? So we move down here. We can also go the reverse process. So we have 0.035 moles of our sugar here, and we want to know how many H atoms. So we actually have to go one step further. So what we do here is we say here, we have 0.350 moles of this sugar compound C6H12O6, and we first need to get it into molecules. So what we need to do, we need to cancel out moles on bottom, and on top we can get it into our molecules. Now this is molecules of our sugar, and to save some space here just above this, I'm going to write our sugar molecules C6H12O6, and just to remind you down below here, this is moles of that sugar compound. So for every 1 mole, again, just like we had in Avogadro's number, there is 6.02 times 10 to the 23rd of these values. So we have 6.02 times 10 to the 23rd. And then the question asks not just molecules of the sugar, but we need these H atoms. And so what we need to do here is, right now we're in molecules of this sugar, C6H12O6. We're trying to get to atoms of H. So we got to do one further thing, and we got to use our formulas here. Now, for every one molecule, this right here is considered our one molecule of sugar. For every one molecule, we look and we find out, hey, how many hydrogens are there? Well, there's 12. So we put down 12. Now, again, this is written, I'm going to rewrite this so that you can see it better. But this, again, is 6.02 times 10 to the 23rd molecules of this particular compound. So what we do here is this. We take 0.35, so we have 0.350, and we multiply it first by 6.02 times 10 to the 23rd, and we also multiply it by 12. So we get a value of, when we round it, 2.53 times 10 to the 24th. So we would get 2.53 times 10 to the 24th, and this is atoms of H. So this is atoms of H. All right, so we've used Avogadro's number to get to this point here. Now that we know a little bit about the mole, we can get into depth and in detail about what we call the molar mass. So we'll transition here. We'll go to the next page of notes, and this is with our molar mass. Now, the molar mass is defined as the mass in grams of 1 mole of a substance. And the molar mass is going to have a unit of grams per mole. Now, a really important point here is this. The molar mass of a molecule is numerically equal to its formula weight in atomic mass units. And so simply the molar mass is found by taking the sum of the molar masses of the atoms in that particular substance, or in a particular substance. So let's go through a couple examples to be able to determine the number of moles in the particular substance. So the first thing that we have to do here is we have to find the molar mass of this particular substance. So I'm going to write the molar mass over here to the right of our sugar. So the molar mass here contains carbon, contains hydrogen, and then contains oxygen. And remember, we just look up the mass that's listed on the periodic table. So for carbon, we have 12.01. So we have 12.01, and this would be grams times the number of moles, which is equivalent in this case to 6, or the number of atoms in that mole. So it'd be times 6 moles. And we could calculate that out. And so if you put in your calculator 12.01 times 6, you get 72.06. So 72.06, and that would be grams per mole. Not a space there, so I'm not going to squeeze it in. We do the same thing for hydrogen. We find the molar mass, or the atomic mass for hydrogen to be 1.008, so 1.008 grams, times the number of moles of hydrogen, which is equivalent to the number of atoms here. So that's 12 moles. And so in our calculator, what we would do is we would type in 1.008 times 12, and we would get 12.096, which I'm going to round that to 12.10, and that would be grams per mole. Now, our oxygen here, we do the same thing. So we look up oxygen. The atomic mass of oxygen is 16.00, so 16.00 grams times the number of moles which is equivalent to the number of atoms. So that is 6 moles. So we do 16.00 times 6. And we get 96. And now to keep consistent, I'm going to say 96.00. So I'm going to add these together. So I'm going to take, in my calculator, I'm going to take 72.06 plus 12.10 plus 96.00. I'm going to press enter, and the molar mass for my sugar compound here is 180.16, and this would be grams per mole. Okay? Now, we can use this to calculate the number of moles in 5.380 grams. So what we do, we always start out by writing down exactly what is written. So 5.380 grams of our sugar, C6H12O6, is multiplied, or we set up our conversion factor to have grams, the diagonal unit, cancel out. So we're left with grams C6H12O6. And then look here, we can go from grams to moles, so we can actually have a direct conversion to moles of C6H12O6. And again, we turn to our conversion factor. So whenever we find the molar mass, this is for 1 mole. So in this case, right now, we're going to have 1 mole. Now the number of grams is what we just calculated. So we have 180.16. Now to find this particular problem, or to answer the problem, we're going to take 5.380 and we are going to divide it by 180.16 and press enter. Now remember, we had 4 significant digits in our problem, so this would be 0.02986 when we round it. So this would be equal to 0.02986, and that would be in the units of moles of C6H12O6. All right, now we're going to do a very similar thing, but I am going to go ahead and give you the molar mass of calcium nitrate. So remember, this can be found using the same method, but the molar mass for calcium nitrate, and you can look this up in notes, we actually did this, is 164.10 grams per mole. And you can go through the process and do the steps like we did in the problem above, but calcium nitrate has the molar mass of 164.10 grams per mole. So again, we say, hey, we want to know the number of grams and 0.433 moles of calcium nitrate. So again, we start out by putting 0.433 moles of calcium nitrate, and we set up our conversion factor. Again, most important thing here is that our diagonal units cancel out. So because we have moles here, we want to have moles down below. So we have calcium nitrate down below, and on top we can go straight from moles to grams, and we're trying to get to grams, so hey, let's go ahead, let's put grams of calcium nitrate. Okay, now again, in this case, 1 is always going to be associated with moles, and then the number of grams is what we calculated, or in this case what I gave you. So we have 164.10 grams. So all we need to do to find this particular problem is take 0.433, came from the number of moles given, and multiply by that molar mass of 164.10, and we press enter. So remember, we had 3 significant digits, so this would round to 71.1 grams of calcium nitrate. So again, all we're doing is we're using the molar mass to convert from one substance or one unit to another. We're just doing unit conversions. And so what this does is it's really important because it allows us to perform stoichiometry. And stoichiometry is one of the fundamental ideas we have in chemistry. It actually ties together quite a bit of chemistry that we've already talked about. So, with stoichiometry, we have it defined as the quantitative nature of substances consumed and produced in chemical reactions. So, with stoichiometry, it's going to be built upon the understanding of atomic masses, chemical formulas, and the law of conservation of mass. And I want to put one key thing down below here, and that is this. Coefficients are key to stoichiometry. So again, coefficients are key, and you'll understand that here in our example. So our example says determine how many grams of water are produced in the oxidation of 1.00 grams of C6H12O6. So first off, we have to think about where are we going, or what's our roadmap in this particular equation. Well, we start here with grams of C6H12O6, and it says, hey, how many grams of water, way over here on the right-hand side, are produced? So what we first have to do is we always have to convert to moles, because if we don't convert to moles, we cannot deal with coefficients. Remember when we balance chemical equations that what we were doing is, yes, we were abiding by the law of conservation, but more importantly here for stoichiometry is we are saying these numbers out in front are those mole-to-mole ratios. So remember that coefficients are key. Now, to save a little bit of time, because you've already calculated the mass in an earlier problem, the molar mass of C6H12O6 is 180.16, and we already calculated this in notes, but that is 180.16 gram per moles. Now, what we always do, we always start out with what's given. So we have 1.00 grams of C6H12O6, and the only way we can use these coefficients is we got to get to moles of C6H12O6. So what we do, remember, we always start out and we cross cancel. So we have grams of C6H12O6. Now, we're trying to get to grams of water. Well, hey, you cannot go from grams of one substance to grams of another. You first have to go to moles of that particular substance. So, in this case here, we have gram to mole, or mole over gram. Whenever you see that, you have to use that molar mass. So our molar mass, remember, in this case, 1 is going to be associated with moles, and we have 180.16 on bottom. Now, we're in that mole-to-mole ratio, okay? So what we can do now is we can go from one substance to another. We can actually talk about that defined quantity and conversion from one quantity to another. So again, moles, because it's a diagonal unit, have to cancel out. Okay? Now, we cannot go from moles of one substance to grams of another. So what we do here is we actually go to moles of water, because we're eventually trying to get to water, and where we find these values are up top here. Okay? So the coefficient is our mole-to-mole ratio. So out in front of our sugar here, there is a coefficient of just 1. And out in front of water, there's a coefficient of 6, which means there can be 6 moles. Now, the last step here, and to help save you some time here, the molar mass of water is 18.02 grams per 1 mole. And so again, we go from moles, we cancel out moles, H2O on bottom, and now we can go moles of one substance to grams, just like we have here. So grams of H2O. And where we get that value is right from that molar mass. So again, whenever you see gram over mole or mole over gram, mole is going to have 1. The number of grams is what we calculated here, so 18.02. And so all we have to do is we have to perform this calculation correctly. So what I like to do, and people can do this differently, but I like to multiply everything on top. So I'm going to start out with a parenthesis. I have 1.00 times 1 times 6 times 18.02. Close my parenthesis, press enter, and then I'm going to divide it by everything multiplied on bottom. So on bottom I have, again, open that set of parentheses, 180.116 times, we have times 1 times 1. Close the parentheses, we press enter, and in our number value here, we get 0.600 grams of water produced. So this whole reaction involving 1 gram of our sugar produces 0.600 grams of H2O. And that's how we would utilize our stoichiometry to go from one substance to another. The key thing is right here. We have to get substance from moles to moles to be able to convert to a different substance. That's the really important part about a balanced chemical equation. So let's go over one more problem that deals with going start to finish of actually doing the balanced equation to actually performing this calculation. So we go here and our other stoichiometry problem. Lithium hydroxide combines with carbon dioxide to form solid lithium carbonate and liquid water. We want to know how many grams of carbon dioxide can be combined with 1 gram of lithium hydroxide. So what we start out with is our balanced chemical equation. If you don't have that, then you might as well not even try the problem. So lithium hydroxide is this. Remember, lithium has a 1+ charge, and hydroxide has a OH-. So when we form this, we have lithium hydroxide. And it is aqueous. It is dissolved in water. And it is combined with carbon dioxide. Now remember the naming protocol. If we have prefixes, we have to name that appropriately. And so carbon dioxide is going to be a gas. Now it says it reacts to form solid lithium carbonate. Okay, so lithium carbonate, remember, just to remind you here, lithium has an Li 1+ charge. Carbonate has a CO3 2- charge. So when we form lithium carbonate, we would get Li2CO3, and they said, hey, that's solid. And then we add to that liquid water, which liquid water is just H2O with an L behind it. Now, can't quite get to the stoichiometry yet because we got to balance the chemical equation. So we start out with lithiums. Well, on the left we have 1, on the right we have 2, so we need a 2 in front of lithium. Now, what we will do, I'm going to skip over the O's for right now because they're going to wreak havoc. But I'm going to move to the H's. I have 2 H's on the left, 2 H's on the right, so they're good to go. C's, I have 1 carbon on the left, 1 carbon on the right, so they're good to go. And now I'm going to get back to my oxygens. Okay, so I have 2 oxygens from this first reactant plus another 2. So 2 plus 2 is 4. And over here I have 3 plus 2. So right now this is balanced. Okay. Now, what I want to do, I want to get to grams, or start with grams of lithium hydroxide and see how many grams of carbon dioxide it can fully react with. So what I do is I start out with the number that is given, 1.00 grams of lithium hydroxide. Now, lithium hydroxide, the only thing that we can do with this, is we first need to convert to moles of lithium hydroxide. So to do this, what we're going to have to do is we're going to have to cancel out grams of lithium hydroxide on bottom, and then again, we have to go to moles of lithium hydroxide first, because, hey, unless we're in moles, we can't utilize our chemical equation here. So, gram over moles. Remember, we find the molar mass. So, lithium here, lithium has a molar mass of 6.94. So, on my calculator, I'm going to put 6.94 plus 1 oxygen. That O, that 1 oxygen, remember, has a molar mass of 16, so 16.00, plus hydrogen, which if you look on the periodic table, has a molar mass of 1.008. So I pull that into my calculator and press enter. The value here for the molar mass is 23.95. And so, again, lithium hydroxide, if you want to make a side note here, it is 23.95 grams per mole. So that means the 23.95 goes on bottom, 1 mole goes on top. Now that I'm in moles of lithium hydroxide, I can utilize my chemical equation and I can go from one substance to the other. I can go from moles of lithium hydroxide to what I want, but it has to be in moles of that same or that different substance. Now, mole over mole, where we turn to find numbers is the balanced chemical equation. This is why we balance. So in front of lithium hydroxide, there is 2 moles, and in front of carbon dioxide, there is 1 mole. Now, I have to go one step further because I want to see, hey, how many grams of carbon dioxide? So again, I have to cancel out moles of carbon dioxide, and because I'm already in moles of carbon dioxide, I can convert to grams. So gram over mole. Whenever you see that, we turn to the periodic table. Now, carbon. We have 1 carbon that has a molar mass of 12.01. So I put 12.01 plus 2 oxygen. So in parentheses again, I put 2. Remember, the molar mass of oxygen is 16.00, and we press enter. So the molar mass of carbon dioxide, I'm just going to draw an arrow here, is 44.01 grams per moles. So we put 1 mole. Whenever we have gram over mole or mole over gram, 1 is always associated with moles, and then that value for grams becomes 44.01. Okay, now what I do, again, there's a couple different ways you can go through calculations. I like to multiply everything on top, divide it by everything multiplied on bottom. So what I do in this case here is I take 1.00, and let me put a parenthesis here, 1.00 times 1 times 1 again times 44.01. Okay, close the parenthesis, press enter. Now, I divide it by parenthesis, very key point here. The molar mass, 23.95 times 2 times 1, and I press enter. So the number of grams of carbon dioxide that can be produced here is 0.919. So that is the number of grams of CO2. All right, key thing here is, remember, the only way I can go from one substance to another is to get it converted to moles first. Then, mole over mole, I can utilize that balanced chemical equation. So take your time, make sure units cancel out. You end up getting what you want on that top location here with stoichiometry. And key thing, can only go from one substance to another if it's moles to moles. Got to get it in moles. That is very essential for this process here. All right. I hope you have enjoyed this episode. Had a lot of chemistry involved in this, a lot of key parts of chemistry. And as always, subscribe.